Hello, everyone. Welcome to the Streaming Alchemy Show. I'm John Mahoney, and on today's show, we're going to be taking a look at the components that make up your traditional live streaming rigs, the video optimized computer systems. And we're really going to be focused on the four primary components that people can really think through as they are going to build their computing rigs, whether that's themselves or work with a knowledgeable provider to put these types of systems together. So, before we get to that, I want to remind everybody that we'd love to have you join us here on the show. So, if you'd like to call in and become a video guest here, just connect to the URL on the bottom and, we can walk in and get you on the show. Otherwise, I'd love to, have any comments, questions, or feedback, through the comment section, and we'll address them as they come in. Also, remind everybody that at the end of today's show, we will again be staying for an after show, a post show uh, get together where it's a little freer and we can talk about any subjects you want. So let's get started taking a look at what goes on with building a computer focused on live streaming. And probably for most people, the first place you're going to think about is CPUs. And that's probably logical. The CPUs are going to be sort of the heart of any production system you put together. And there are a lot more choices today than there were even a few years ago. So there's a lot to discuss there. But equally important is what are now called GPUs. It used to be the graphics card, and a lot of people still refer to them as that, but they've grown past that. So these become much more as generalized or graphical processing units. There's different terms for it, but they're highly efficient math processors that are part of your graphics card. And so, again, a lot of choices on that front as well. The next thing is memory, and memory is one of those things that we tend to take for granted. We just, say, "Oh, I need this much RAM, and I should be good." But there's a little more detail behind the different memory choices you have, and it's definitely worth, paying attention to what the specific characteristics of the memory you put into a system are. And finally, there's storage, which is sort of the unsung hero of it all, because we're generating so many terabytes of data with video, and we have to have a place to handle it, not just long term, but also transactionally. As where do I record? Where do I basically put all my assets that I want to use and stream from it during a production? So, again, a lot of choices and a lot to talk about around storage. But like I said, the first place to start is with CPUs. And probably the most logical thing would be to just understand what CPUs actually do. Uh, they handle all the general compute tasks inside a computer. And that's everything from, once you're, past the initial post and into boot up, that's handover to the CPU. A lot of IO runs through the CPU. So everything you want to do from printing, some network things, other types of access to USB. A lot of those depend on the CPU to facilitate that. And of course, a lot of the reading and writing from memory also involves the CPU as well. Uh, and it also interfaces with the other hardware in the system through what they have is called firmware, basically little ASIC chips or other programmable chips on different components you plug into a computer that all provide the smarts for that particular function, but need to talk to the CPU to communicate whatever they do with other components in the system. So again, a more low-level view of some of the things it does. And it really coordinates the activity. So it doesn't necessarily have to do everything on its own, but it certainly is involved in coordinating things, letting people know when they can talk inside the system and, how that data flow gets managed. A lot of that involves the CPU. But where you actually end up sort of running up the clock on the CPU, all the things that are heavy lifting, it's running the operating system. And anybody that's worked with Windows and Windows 10 these are not lightweight OSs anymore. There's a lot of density, a lot of layers. So the performance of your CPU does matter in the overall performance of the system. And the CPU also runs all of the software programs you're going to use. So, it could be vMix or Wirecast. Uh, Even on dedicated boxes like the TriCaster, it's running that software, and a lot of that is running at least initially on the CPU, but with help from other components. And there's a lot to consider though when you are thinking of CPU performance and capabilities. So the first one is something that are called computing cores. Now in the distant past, your CPU used to be just one computing core. It just did its thing and everything happened, sort of in sequential order. So as a program would run, it would feed instructions to the CPU, which would then execute those and grab the next instruction. But as computer systems have become more complex and programs more sophisticated, those things no longer needed to be serialized. There were lots of things in a computer that could run in parallel. So things in the operating system and IO bound could also run alongside things that were running in specific applications and other things transactionally with the network that we're talking about. So multiple things running. Oh, Richard, thank you for joining us. So when you look at this, essentially the answer was, as opposed to developing faster CPUs in general, it was develop CPUs with more cores, effectively a big wrapper around multiple smaller CPUs that each could run specific tasks in parallel with others. And that has a huge impact today. This is, in a lot of times when people talk about it, they talk about multi-threading, which is the ability of a program to break off what it needs to do into multiple parallel threads of computing. And that's where multiple computing cores really shine. Now, the other piece that goes with this is something called hyperthreading, which people sometimes confuse with multi-threading, but they're really unrelated. What hyperthreading does, it's an optimization for each one of the cores that's found inside a modern CPU. And so the best way to think about it is that with hyperthreading, there's a component in the CPU that is watching that core and basically is saying, if that core gets busy with one execution thread and then has to pause it, I'm going to jump in with another execution thread right away and let it run. So it effectively keeps that single core in the CPU as fully occupied as possible with compute assignments, regardless of whether one has to stop or the other. It tries to keep that core piece running all the time. Somebody explained it to me in a way that I thought was kind of humorous. They said, if you want to think of the relationship between cores and computing, a computing core is like the mouth and hyperthreading is like the hands. It's what you need to feed it and make sure it's constantly fed, but one at a time still to the mouth. So Ken, thank you for joining. Seems like we have a lot of activity from Northern California. So I'm glad you guys could be part of this. So the next thing to think about after the cores count and the hyperthreading capabilities is something called the base clock and the boost clock. Now, again, this is something that's changed as CPUs have evolved. And the clock basically is the speed that instructions can be processed inside a computer. How many times a second does the CPU get to do stuff? And a lot of this in traditional space is based on electronics and sort of the time it took in a digital system for the system to become stable when it made a transition, a state change. And so that is effectively this. It's saying, what is it that, how fast can this computer run? And to make sure that anytime I need to take a snapshot of what's going on, it's stable and solid. And that's what your computer clock does, the CPU clock. But they become even more sophisticated. They have something called a base clock and a boost clock. And so the base clock this is the speed that the CPU will run, or a core in the CPU will run at all the time. So it says this is sort of a safe speed to run at. Then it also has something called the boost clock, which is basically the CPU going and saying, I'm going to overclock myself. I'm going to run faster than I really would normally run to satisfy certain immediate demands from the system for processing. But then I have to retreat at some point back to my boost clock, my base clock. And that's driven a lot by thermals. Now, how much heat is it generating? And what will it need to do to manage that heat on the die itself so the chip doesn't overheat? So the base clock is typically the guaranteed performance with all the cores running at their base speed with all occupied doing computing tasks. And the boost clock is going to be for those exceptional things where I have to jump up and do something fast and then the system backs down again. But both those numbers are important for the types of things we do in live streaming. So the other piece, which is sort of related to the base clock, boost clock component of performance, is single core versus multi-core benchmarks. Now, the reason I put the term benchmarks in there is that different programs depend on different aspects of a CPU. Some programs, especially things like gaming, which is not the space we're really focused on, are much more single core focused. The performance of a single core probably has more impact than the number of cores and the aggregate performance of multiple cores. But other programs, especially things like streaming applications, are probably much more multi-core focused. So where you'll find the biggest bang for the buck is probably going to be in multi-core performance. But both of these are important metrics when evaluating a CPU. And if you were a gamer looking to live stream, both of these numbers and the balance between them could be really important if you're doing it all on a single system. So the other thing is the inclusion of an integrated GPU. And this will probably be my public service announcement number one. Don't run a live streaming system with the integrated GPU on a CPU. They are going to be underpowered, under-resourced, and it's really going to unless you're doing very light types of live streaming, it's going to let you down. It's not going to be something that you'd want to do any sort of significant production with, or anything that's challenging even in a simpler production. So something to stay away from, but it's again another point that people will use in evaluating CPUs. And what's interesting is a lot of the CPUs out there come in both flavors. You can buy a version with or without the integrated GPU. But one of the things the integrated GPU can give you is hardware-based encoding and decoding. And Intel has something called QuickSync Video, which is an H.264, H.265 encoder decoder on the CPU itself. But it's integrated with the GPU component of the CPU. So it's something that it's a helpful add-on, but it isn't something I'd recommend as your main encoder decoder for everything you do, because there are some limitations, especially around quality, that could have an impact here. So just keep that in mind when you think of performance. But this is sort of the full range of things that you have to worry about when looking at the different CPUs. And there's really two lines of CPUs that are out there in the world today. There's the AMD lineup, which has Ryzen and Threadripper. And there's the Intel, which has the Core i7 and Core i9 series. And for most people, these are going to be the two vendors that you look at for processing. And just to make clear, the AMD line that I'm talking about is okay. Nope. Just wanted to make sure. I saw a message that somebody said it's we had a freeze here, so I'm sorry if I stopped, but I just wanted to be sure everything was good on this end. So The two lineups with AMD and Intel. Intel has been sort of consistent and evolving all along, but AMD has been making some major advancements generation to generation. And so what I'm going to be talking about here is really AMD's third generation of chips, which, in many ways has brought them as a true peer to Intel and a very solid choice for anything you'd want to do with live streaming. And in fact, I'm probably, play a little from the future here, but I'm really psyched on what AMD has available today and where they're going with their lineup. So let's actually, start there and talk a bit about this. So the two lineups are their 3000 series Ryzen chips and the Threadripper lineup. Now, the Ryzen chips actually run anywhere from, in the 3000 series, anywhere from, the lowest end, which I think are 4 core still, all the way up through 16 core chips. And the Threadripper lineup sort of now really, jumps that way up. I believe they have a 64 core and a 128 core sort of lined up here. So very, very, high core count, multi-threaded focused chips in this series. And, if we think about though, even the individual single core performance of the AMD lineup is actually pretty solid. Intel is probably superior in this in almost all their chips, but the single core performance on AMD is very good now. And it really has exceptional multi-core performance, both, in aggregate because they have lots of cores, but also the performance and the way the multi-core architecture of the system of the CPUs work. They are really very efficient in multi-core. And with the high core, I have up to 64, but they actually have in the Gen 3 Threadripper is up to 128 now. I don't think that's released. But very high core count, which means you have a lot of space to grow, within this architecture. And the other thing they have, which Intel hasn't gotten to yet, is PCI 4 bus compatibility. And that's a real techie sounding way of basically saying it's the next iteration of how much data can pass across the bus between the different cards you have plugged in the system and the different components that are talking to each other. It's actually a doubling of bandwidth between PCI 3 and PCI 4 buses. And that has a play. Probably not as much as the marketing hype is going to sell, but in certain areas, that PCI 4 compatibility can make a big difference. So we'll touch on that later. And the other thing about the AMD lineup of CPUs is from a price performance point of view, they are really excellent. Almost across the board, you get equivalent capabilities for probably 30% less compared to the Intel equivalents. And so it is definitely, something that if you look across this, there really are a lot of great choices. But to my mind, the best, the sweet spot in this lineup is probably their 8 core, 16 thread 3700X processor. And I mean, the amazing thing about this is you're talking a processor that's probably under $350, in terms of general availability, what you can get it for. And, I'm making a point here that I'm talking about the Gen 3 processors because it'll be a 2700, which is their Gen 2 processors. And that's something that I would not go for. There are architectural improvements that were made that really avoid some bottlenecks that were in the older Gen 2s. So this as a processor, I think it would be excellent for almost everyone that has, general purpose live streaming needs on the higher, more complicated end of the spectrum there. So if we look at the Intel line, now Intel is on their 10th generation of CPUs. So and they've been around, 25, 30 years as sort of the leader in this space. So a really long legacy. And I think, that's actually played a lot into some of the capabilities that the Intel lineup has. And one of those are higher clock speeds. In most circumstances, the equivalent Intel chips will have slightly higher clocks, especially, the between the base and the boost clock speeds. you probably will get better things coming out of the Intel lineup, but again, at a premium price for that. Uh, and it definitely has the single fastest core performance for almost all of their CPU lineup. And, again, they do have solid multi-core performance, but I think both in terms of number of core availability in it per chip and the performance of the multi-core architecture, you probably are better off looking at the AMD line compared to the multi-core performance on the Intel lineup. Uh, but the other thing they have is really broad industry support. They've been around everywhere. And so you're going to have a wider choice of motherboards, cooling solutions, other things to sort of go into the ecosystem around a CPU. And that is definitely something to consider as well. Uh, and the other thing which I had mentioned is about built-in video encoding and decoding. That is a feature that's found on Intel chips and not AMD chips. So well, I wouldn't use that for certain things, that we would be doing. One of the things that does leverage that encoding is the latest versions of NDI. So this would be one of those things where you can, make a decision of what makes the most sense. But it's definitely something to factor in because NDI will leverage the QuickSync video on Intel chips for the encoding and decoding as one of several mechanisms it uses to do hardware encodes and decodes. So if I were to look across the Intel line and sort of try to pick a sweet spot, I don't think at this point in time that Intel has one thing which I say is their, best dollar performance value. But if you're looking for a solid chip that can do high performance computing, it would probably be the i9 9900KS. And the thing that the KS has is it lets you have all 8 cores. It's an 8-core chip. All 8 cores operate at the 5 gigahertz boost clock simultaneously. So it means that under very heavy loads in these types of multi-threaded environments, you can do very well with performance using this chip. But it is still this chip, compared to the $350 price point for the 8-core Ryzen, this chip is going to cost you probably about $550. So a significant jump and still the same core count. So there may be situations where this will make a big difference to your streaming performance and the overall system performance, but it's something that I think you'd have to weigh and make sure that it made sense, vis-a-vis the AMD lineup. So this is probably a good overall view of the different choices you're going to have around CPUs. But equally important in everything that we do here is GPUs. And maybe even more important in some ways for the overall performance of your system for live streaming. So what a GPU does is, obviously it handles general display related functions, but its biggest advantage is that for a lot of mathematically intensive things, it can take the computational load off of the CPU, which means the CPU can focus more on administrative things, the flow of data and communications and other things that sort of take place in the back end. And a lot of the computational things can actually, can actually handle some of the streaming, compositing, other types of video transformations that need to take place on the live streaming side. So it definitely makes a big difference there. And this computational muscle of, Ken, he's talking about his 4-core Xeon laptop maxes out at 4 NDI-HX cameras. Yeah, NDI-HX is a funny beast. And I think to a certain extent, Intel is back, New Tech is backing away from sort of the approach they took because NDI-HX2 is much closer in architecture and design to full NDI, even though I know that's not something New Tech sort of promotes as the way to describe it, but high bandwidth NDI. So it's something that I think architecturally might get a lot better going forward with NDI-HX2. But I mean, at this point, we all have NDI-HX cameras and converters and other things, so that's not going away. So, to Ken's point, it is something, that you're going to have to consider, with the systems you put together, the types of components you're going to need to deal with and the protocols around that. And but that is one of the things actually where GPUs really shine because they are computational mathematical engines. What they've done is they pared back a lot of the broader logic in a general CPU, and they've really focused it on these graphic transformative types of functionality that is a part of the creative arts on computers, but very much so around things we do in live streaming. So, that's something definitely to keep in mind as you think about the types of productions you're going to want to do. And the other thing is these GPUs also provide hardware encoding and decoding. And let me just take a step back because this tends to be some confusion around this because people talk about NVENC and NVDEC versus other things that those capabilities inside a GPU don't really handle. So the GPU itself has a set of processing cores. So on different lineups, they call them different things: CUDA cores, stream processors on the AMD lineup. But those cores are really focused on the mathematical transformative things. So if you think of video when you're streaming video, I'm resizing things all the time. I can do a picture in picture. I can do graphics and put them as overlays. All of those things are taking basically huge bit fields and doing all sorts of transformations to get the layering correct, to get sizing correct, and to make sure all that stuff looks right and it's doing it in real time. That's based on the cores inside the system. When I need to stream, when I need to write out and record data to a disk, that's using encoding. So the encoding capabilities of a GPU are going to help with those things. The core capability, the processing capability are going to help with the other things. So it's something to think of as you talk about the different types of uh, GPUs that you may want to leverage. But definitely, they are two distinct aspects, both very important to the live streaming experience that your viewers will get. So when we talk about performance, we just sort of touched on this. Again, these are computing devices, so everything is clocked. And so higher clock frequencies are going to typically result in higher performance, certainly within a similar GPU architecture. Uh, the other thing is the width of the data path. Now, this is something that most people don't talk about, but the data that gets onto your GPU has to come from somewhere else. So when I'm streaming, it's using the PCI bus to pull that data, orchestrate it by the CPU out of memory and into the GPU to process and then back into memory. Uh, the width of the data path is basically saying how many bits per clock cycle can I suck onto the GPU and push off of the GPU so you can actually show it to somebody and do something with it down the processing pipe. So very, very important component to this, but it's something that's usually overlooked. And so this can be anything from 290 bits to over 1,000 bits that come in. So between the two, the clock frequency and the data pad width, that's going to talk about how much you can get on and off of a GPU. The other piece is the speed of the internal memory that's on these GPUs. And for the most part, faster memory is better, but you do get to the point where that fast memory becomes frighteningly expensive. And so for most applications, the standard, GDDR, 4 or 3 on the common GPUs is going to be something that you'll probably be fine with. And that's not going to be something where you necessarily have to go for the highest speed memory, but something to consider in terms of overall performance. The other piece is, I mentioned, the processing architecture. As cards have evolved over time, they usually adopt an architecture for a family of cards. So in the NVIDIA line, they have, like, currently it's Turing, but they had, Kepler and Maxwell and Pascal, and all of these were different architectures, in addition to being great scientists. And each one added something new or enhanced the capabilities in the processing. So in the current Turing architecture, you have the ability to do things like real time ray tracing. So actually doing things like shadows and light reflection, refractions off of objects, all that stuff in real time in hardware. So these are the types of things that gamers love. Uh, Potentially, it could make a difference in some of the things that we do as live streamers, but that's probably not something that's going to have a big impact. But there's also in the latest generation things around AI processing, how it's able to take and upres the apparent visual quality of an image using AI and sort of snapshots of this would be a very high quality image. And now I have lower resolution renderings and comparing those two to make those lower resolution renderings look a lot better. Now, that scenario, though it isn't in anything yet that I'm aware of, could definitely have an impact on what we are doing, especially in more constrained bandwidth situations. Anything that could up that quality that the viewer of what you're producing sees is definitely a plus. And some of that, are going to be based on things inside the architecture. So look at these things as you think about what GPUs make the most sense for you. There's also dedicated processing capabilities. So those are some of the things that I just mentioned, along with, the encoding, decoding things that are baked into the ASICs on the programmable chips on these GPUs. So again, there are two big players here, AMD and NVIDIA. So if we're starting to look at this, I'll get this out of the way. Where I loved AMD in the CPU side, they are really at this point still an also ran in the GPU side. But they are the only vendor that is compatible with Macs. So, there's some good things that they have, and I just want to go through it. But consider this whole discussion only relevant to people if you're on a Mac. Uh, so they have a stream process account, which is those compute units I was talking about. So they're very good in that, and they have very fast memory clocks. And high speed memory are baked into this. That, as I said, I don't think is going to have the same impact with a lot of what you do. They have very wide data channels. So these are, significantly wider, in many cases, far more than double their counterparts in the NVIDIA lineup. And they are relatively affordable. And, I stress relatively because none of these GPUs are particularly cheap. So the reason you would do this at present is only because you're running Wirecast on a Mac or OBS on a Mac. And this is, the best option you have for GPU processing. Scott, hello, welcome here. Let me make a point. Outside of, people who can afford the new Mac Pro or using very old Mac Pros, there's no way to put these graphics cards directly into a system. But recently, probably the last few years, there's been more focus on things called eGPUs, effectively Thunderbolt 3 connected cages that can hold a GPU in it and are recognized by the operating system as a GPU. So this is really the use case. Most people would have something like a MacBook Pro, an eGPU, Thunderbolt 3, and plug a graphics card in and use that to power the processing for a lot of their live streaming. But keep in mind now, all of the things we talked about with, faster memory and, wide data channel, that all gets shrunk right down to what you can do on a Thunderbolt 3 connection, which is going to be, in most cases lower than this, and there's latency in the communication, so there'll be some delay from all of that. So it's not an ideal solution, and I'll say it right now, and I know I'll probably get a lot of haters. I'm not saying you can't do live streaming on a Mac. I just think that if you're starting out and you're looking at alternatives, you have more alternatives at more cost effective, higher power, uh, you know, packages uh, going in the Windows Intel line versus the Mac. I love Mac. I do a lot of my work internally on Mac, but just comparing it for everything, we're going to talk about with live streaming, it's probably would be my second choice. But in almost all cases, the first choice is the one you got. And if you're using Wirecast on a Mac or OBS on a Mac, go for it. And this will be something that could potentially help up your game and get you up to that next level. So the next, two lineups we're going to look at are going to be from NVIDIA. And the first one is their GeForce lineup. And the GeForce RTX, because they have GTX as well. The RTX is their latest lineup. Those are the ones in Turing lineup, where all the architecture, so all those features are in these types of processors. So I think, the biggest thing NVIDIA has going for it is it has CUDA support. That's its core processing engine. And CUDA is broadly supported. I mean, there's so many applications out there that leverage it. And so even beyond live streaming, if you're in 3D visualization, virtual reality, the number of software applications that support CUDA are going to vastly outnumber anything else. And so definitely something to consider, but it's also the most broadly and most deeply supported GPU uh, framework in the live streaming world. So Wirecast supports it, and most of the deeper integration has taken place on Wirecast with uh, the CUDA capable GPUs. Uh, I know it's OBS. I know vMix. TriCasters use CUDA cards in them. So across the board, it tends to be the favorite GPU architecture for most software vendors. And that really makes a big difference because it doesn't matter ultimately how great the card itself is. If the great features in the card aren't supported by the software that you want to use, it doesn't do you any good. So you're not really buying hardware, you're buying better performance for your software. And that's really the way in any of these things you should think about what you're doing here. So the other thing is NVInc and NVDEC are really good quality, certainly at higher bit rates. You may find that the quick video sync on the Intel lineup as a hardware uh, software decoder may work better at lower bandwidths, like really low bandwidth. But for some of the higher bandwidth stuff, I think across the board, people would say the images generated by NVInc and NVDEC are going to be superior. And I can tell you from our own internal development work that we've done here, H.265 coming off of uh, these encoders is really impressive. So definitely great bang for the buck here as well. Uh, and it really has, a solid price performance thing, which, unlike, in the Intel case where they tend to just be across the board really premium pricing, there are great options across the entire GeForce RTX lineup. And so based on whatever you do, you can find one that probably it fits at a price point, that makes sense for you business wise. And I think, you know, that's really the reason I would recommend these for almost anybody that's going on a non-Mac system. And I would even be very comfortable recommending the previous generation, which was the GTX lineup, the 10 series. So anything from the 1050 Ti on, I think would be really great performers in the uh, in a live streaming system. And, certainly if that's something you have, I wouldn't go out and buy a new one unless there was a compelling reason. Any of these cards could do a really good job. And, I think the other thing, there was another GTX card out there that this is one of those weird things. NVIDIA came out with the RTX lineup, which is their 20 series. And they also came out with another GTX card, the GTX, a series of cards, the GTX, I think it's 1650, 1660, and then a super one of those. So like three cards in that lineup that are all based on the new Turing architecture, but don't have any of the additional ASICs for the AI or the real time ray tracing. So that lineup is also something to consider. So if you're out there, the GTX lineup, but there isn't a huge price difference between the GTX and the RTX lineup for the most part. And so I'm not sure whether there's a great incentive to move to that if you're using it for live streaming, but definitely consider it when you look at all the different options you have here. So the things with NVIDIA though don't stop at the RTX line. They also go into something called the Quadro line. Now, Quadro cards are the big monster GPUs for the scientific and visualization community. So very, very fast memory, very, very high quality builds. And in fact, one of the things you'll notice is they are really well architected from a hardware perspective, and the cards themselves are actually only take up one slot. So if you're in a tight build, the Quadro cards, I believe almost across the board are going to be single slot cards, and that gives you more space. But the build quality is really exceptional compared to what you have in the RTX line. And the other thing about them is they have unlimited hardware encoding. Uh, Now, the GTX line or the RTX line that we talked about with the GeForce has unlimited decodes using NVDEC, but you're limited to two encodes with the NVEnc. Now, I know there are software ways to get around this, but sort of it's whatever you're comfortable with. But from a licensed point of view, you buy the card with the understanding that you use it within the constraints of the license, and so the licensing sort of says you get two, and it's not two per card; it's two per system. So I could have five of these cards in a system, and I still get to do only two encodes by license. Your mileage may vary if you choose other routes, but in the way we do computing today, this really is something to consider. Uh, and with everything else I talked about on here, I mean, the higher build quality can be a reason to go with the Quadro lineup, but they are significantly more expensive. Probably close to double in some cases the cost of their equivalent compute powered card in the GeForce lineup. So one of two things is going to make you do this. Either the reliability. I mean, if you are really abusing your system, bringing it into tough places, shipping it around all the time, thermally challenging it, you will probably have higher reliability with the Quadro than you would have with the GeForce. But I don't think it's really worth that. You'd probably be better off carrying a spare card with you, if that were the main driver for it. The one area where it really makes a difference is in the unlimited encoding. And like I said, I know the software is out there, but given the number of things that we do today that we weren't doing in the past that require encodes and decodes. So first you have multiple streams that you can put out in a lot of systems today where each one can be its own format and would require its own encode. You can do SRT, which requires encoding and can require multiple signals to be encoded simultaneously. And the other is WebRTC, which again does encoding and decoding to bring in remote guest. So if you have systems that support these things, you'll have something in there that can leverage the hardware encode and decode, value of the Quadro lineup. So so, yeah, I mean, Richard, I've seen some of the photos you put up on Facebook, and yes, I see you a lot at beaches. So it's sort of like you're abusing your equipment or you're pampering yourself. I wasn't sure which way that went, but yes, I have seen some of the things you're doing. So, that's I think in terms of looking at the options in terms of GPUs. This is probably the space of the range of options you're going to consider in almost all cases. But that's only half of it. And I know we're running sort of long, so I want to make sure we don't run too far over. But the other piece to all this is memory. And memory is one of those things that's really the forgotten component, the last minute. Oh, yeah, and I want this much memory, so throw it in there. But there are certain things to consider about memory that could impact, the overall system performance. So what memory does is it provides fast short-term storage, which means anything that comes into, like everything's read over the network, that's pulled into capture cards, that's processed off the GPU, that stuff is all dumped into memory. And it sits there for the amount of time it takes to do the next thing with it. So you have to make sure you have enough memory to handle everything you have going on there. It also stores all the running applications. So the code that's sitting there is usually all sitting in memory. And if it's not, your system is going to be performing slower than it needs to. So you definitely should have enough memory to hold all of the active programs that you're going to be running. Uh, and as I mentioned, it's where everything gets dumped. So it's how programs exchange information as well. And I have to move data between things. It usually ends up getting dumped in to your system memory. But when we think about memory performance, that's something that we don't give as much consideration to. But like other things, memory has, it's computers, it's clocked. So it has a clocking frequency. So what the clock frequency means is how often can a memory card provide or read data from the bus on the system. And basically the memory cards are mostly 64 bits, so it's like 8 bytes at a time. So that's what it's reading on and off the card. So definitely impacted by the clock frequency of the card. There's also, if you look at memory, they have things called timing metrics, and I'll go into it a little bit, but this really talks about the latency with when I need to do things with memory. What are the latencies between asking and getting it to do it? And so those timing latencies are somewhat important, but not overwhelmingly so. So I'll go into that a little bit more in the next slide. The other thing that impacts performance is actually not part of the chip itself, but is part of the motherboard. How can the motherboard access this memory? And there are different ways that it can set up channels to do that. So something else to consider, not necessarily about your memory specifically, but can inform the decisions you make about the memory you want to use. So the first thing to look at, when you see memory and you look it up, is you'll see something like this over here. So DDR4 4600, and usually in parentheses something PC4 36800. Now, these are higher performance memory modules we were looking at here. But what this is saying is this is DDR4 RAM. So there are generations of the cards, the memory chip architectures that have progressed. And DDR4 is really the current one. Unless you're getting memory for an old system, this is what you're going to be buying. So the DDR4 is telling you it's the latest. The 4600 is the clock frequency. And so that's telling you how often per second in meg. So this is giga. So it's 4,600,000,000 transactions per second. This can do with the data, with bringing data on and off. And so that's, very highly performant. But if you look here, this number is basically just another way of saying that number. And so the PC4 is just saying it's DDR4 memory. Now the 36800, if you remember, I said that the DIMMs are 64 bits, so 8 bytes wide. So what this is saying, this 4600, if you multiply it by 8, magically becomes this. So this is saying I can pull 8 bytes for each clock cycle, and that means this is the number of bytes that I can bring on and off. That, this times a million. This is a meg that I can bring on and off of memory on a given clock cycle. So this is giving you that level of detail there. But the next thing to look at though is timings. And timings come in a little strip of 4 numbers. And if you look at the timings, the first one is the one that is usually highlighted. I think I'll just, it's called CAS latency. That is from the time I tell the chip I want to do something with it, how many clock cycles does it take before it can respond? And that's basically like the wake up time. I need you to do something. It's like, okay, what do you need? And so in that part of the discussion, so that's the one that probably has the most impact overall in terms of real performance that you'll see. The other timings are all around. Memory is stored in sort of rows and columns. It's sort of big square matrix, from an architectural point of view. So when you have to access a particular row, and then get to a column, how many clock cycles does that take? But the thing is, once you're in a row, going through that row is very, very fast. So you have tiny latency there. But then if I have to go to another row, and then move to a column, there's more latency there. So these are the types of things, where you have to understand the latency, the overall latency of a chip. And then, the last latency number is all around the number of clock cycles before it's safe to read the data from the chip for any processing. So some of these things are overlapping. But these things, keep in mind, are clock cycles. So if you have memory that runs at slower clock cycles, at a slower clock frequency, these timings could look better. So these are not absolute. So like a CAS, a CAS 16 isn't going to necessarily be better than a CAS 18. A CAS 18 on a really fast chip could be better than a CAS 16 on a much slower chip. So, keep in mind, but these are things probably won't have a huge impact on what you do, though the CAS latency may, especially for the AMD, if you're pairing this with an AMD chip, because the architecture of the AMD CPUs, I'm sorry, I want to be clear, architecture of the CPUs for AMD depend more on working with memory to gain performance. And so some of these would probably be more of a concern if you were, working with AMD. If you're working with Intel, probably less so, but still something to keep in mind. We talked about the CAS latency. The other thing you'll get is the voltage, and that's just how much voltage this chip will require. And people who do overclocking, which I don't recommend on some of these things, people do overclocking, for their memory, may play with this. Not something you really need to worry about. So the last thing here I mentioned was not specific to the memory itself, but the memory channels on a motherboard. And to really put this all in context, your motherboards today usually work in either what's called dual channel or quad channel. Quad channel tend to be much more expensive and come only on higher end motherboards. But if you've ever built a system and you're always saying, oh, I got to put the memory now together in pairs, and I put one in slot 1 and one in slot 3, then the next one is supposed to go in slot 2 and slot 4, and you're supposed to do so. That's for dual channel, and that's the typical thing you'll see. This is something where I know people say, well, I bought these 4 memory sticks and it was better than getting like 2. And the answer is no, not necessarily. 2 memory sticks is, if you're in dual channel systems, 2 memory sticks versus 4 memory sticks really isn't going to make any difference. As long as you have pairs, then you get to leverage the performance of dual channel. Quad channel, you need 4 at a time. So if you have a quad channel system and you put one large DIMM in there, you're not going to get the throughput you get as if you put 4 smaller DIMMs in there. Same with dual channel. But the reality is quad channel probably isn't going to make much difference for you. And in fact, dual channel probably isn't going to make much difference. We're talking about really, really high speed capacity. And most of the things we do with live streaming are not going to involve those types of bandwidths. So not something I would put too much weight to in looking at, solutions, but you'll probably get dual channel with almost any motherboard you buy. So the next thing is storage. And storage is, again, another one of those sort of unsung heroes. We're generating terabytes of data all the time. And we're always counting on having some place longer term, to put it. So that's where storage comes in. So, storage at base, it holds the operating system and all the installed software. It's the target for where you save files to, where you do your recordings to. So all that stuff is important. And it's also the swap space if you run short on memory. So if you don't have enough memory for all the programs you want to run, the operating system is going to start pushing stuff out to disk. So this is not me recommending getting faster disks. This is me recommending getting more memory. You do not want in a live streaming system, something that needs to be running as a real-time system ever, to be leveraging swap space on a drive. I don't care how fast it is. It's not as fast as memory. This is definitely something you want to avoid, but it is something that storage does. So let's see. So in terms of options, there really are just 3 options that are in the marketplace today, that most people are going to be able to use. One is physical spinning platters. They have a use still. They're not totally obsolete, but not the first choice for most of the things you're going to want to do. The second is sort of those 2.5-inch SSD drives. These basically are little drive replacements. And in some ways, you should think of these as an architectural bridge, because if you open them up, the actual storage inside of it, it's just tiny little chips. It's very, very small footprint inside. This was done really as a way to bridge between the traditional drives, both the 3.5-inch and the 2.5-inch in laptops, and SSD technology. So you can replace one with the other. But it is really just a set of small chips inside this. There's nothing special outside of the packaging. And the other thing now are the M2 SSD drives. And these M2s now are much closer to reality. This is really what you have with SSD. The memory and an interface to that is traditional, that's non-traditional, that just is optimized for data flow. Now, there are a couple of things to consider with performance, though. So rotational speed, how many times per second does and it's only really for physical drives, how often does that spin? So if you're going to do anything with video and a physical drive, it's 7,200 RPMs is sort of the minimum. And it's not a mega or gig. We're talking about physical stuff here. So this is just 7,200 rotations per minute, which is fast for physical things. But that's the baseline that you need for anything you want to do with a physical drive. The other thing is your sustained throughput, your performance over time. So one of the things, I'll put these two together because the other thing is buffer size, which is performance over short periods of time. So the difference you find between lower priced SSDs and higher priced, so the Pro line SSDs, is really around how they deal with sustained throughput versus buffering. If you benchmark some of the lower end SSDs, what you'll find is when you copy a file, they start off really fast and look just as good as the SSD drives that cost twice as much. But then at a certain point, and usually not too far in, a couple of seconds, goes down a cliff, then it's really low sustained transfer. And that's because they use buffering to make up for poor performance. So with buffering, the ultimate thing is that you have to pay for it somewhere. It's like buffering with streaming. You can't just say, well, I have a buffer and I'm going to keep that buffer filled all the time, because it doesn't work as a buffer then. Eventually, once it's filled up, you can't push any more in there and you're back to real time. This is basically as, it can't go any faster once I saturate the buffer. Buffers are great when there's a burst, and then the buffer can sort of flow out the rest of the way behind the scenes. And you just were able to dump a whole lot of data and keep going. And that's the difference. Sustained throughput means this is the throughput it can just do day in, day out. When I'm writing video, I'm looking at sustained throughput. So anything you want to record, anything, that involves, that sort of continuous bit rate at, over time, sustained throughput is the metric you care about. Don't be fooled by benchmarks that sort of leverage the buffering to make drives appear faster. Very important for live streaming. The other thing is the data interface. Now, SATA interfaces developed with physical disks and sort of moved from there. And they are actually fairly limited, even the most advanced ones. You're probably in the, 500, 500 megabit per second transfer speed peaks. But there's, when you moved away from sort of the drive footprint, you also moved away from some of the limitations that SATA imposed. And so with the M2s, a lot of them use something called NVMe, which is basically a unleashed data throughput model for talking to solid state drives. And you can do things over 3,000 megabits per second using NVMe. But there are still M.2 cards that use SATA. So be very careful if you're buying something that which one of these interfaces the card uses, because it makes a big difference. Performance is vastly different between the two, and you definitely should keep that in mind. So the use cases we have here is really, I'll go through it for solid state drive, for spinning drives, physical drives, recording and long-term storage. They're not ideal for recording, but because you can have really big drives, they could be useful. And they are certainly fast enough for most recording needs. And long-term storage, definitely, because the cost per terabyte that you get, which is the way we look at it these days, is really high. So putting that up on a shelf, isn't going to cost you tremendous amounts of money. I would definitely avoid them for your system drive. Your system drive is going to be called on all the time. The operating system is always running behind everything. That definitely should not be a physical drive. The next thing is your SSDs, and these and the SATA SSDs. They're great for recording. Certainly enough bandwidth there. But I'd only use them for recording if they're removable, because you don't want to tie up your streaming machine copying all this stuff off and making it sort of the bottleneck, because I can't pull the drives out and plug them in and pull stuff off to an editing machine later on. But these are perfect for editing. They're perfect for your system drive. And unless you're made of money, I'd avoid using them for long-term storage. It's just really expensive. But no reason you can't if that made sense for you for some reason. And again, the M2 drives with the NVMe interfaces, ideal for editing and processing, great for system drives. I probably would avoid them for recording, A, because they're overkill, but B, because these don't really come in easily removable interfaces or frameworks. So they're sort of tied into, most cases, the motherboard. And that's something that, again, it probably wouldn't be ideal. And they also come in smaller sizes. I mean, you can get SSD, in the traditional format up to 4 terabytes. And I think they might be at 2 terabytes, though I'm not sure in the NVMe M2s. But if they are, that is frighteningly expensive. So keep that in mind as you think of how you'd want to use this. So what would I select? I think that's probably, the question we all should ask as we look at putting a system together. And it comes down to everybody's budgets and requirements are different. And there aren't, if you're working within those parameters, there aren't really, bad decisions if you're picking good components. And I think that's, that's probably what you should do when you put your own list together. For me, and the types of things we do, because we do a lot of experimental stuff around software development, we needed to be able to work with multiple 4K feeds and sources, cameras, video streams, other things. So that was part of my consideration. Uh, we're doing hardware and software, hardware and encoding and decoding uh, all the time, and software encoding and decoding comparatively, to match up to what we see on that. And that's in both 4K and 1080. So we needed to support that. And uh, we, because we're a development house, ultimately, we needed to do a lot more beyond just live streaming. So we needed systems that could do all of that. And we work with tons of NDI sources. So that was another consideration in what we have here. So what our selections were, and with the systems we set up here, is the 16 core Ryzen 9, which is 16 core 32 thread. It's expensive. This is probably $800 or $900 for the CPU, but definitely a great performer for the types of things we wanted to do. Because of the encoding and decoding, we went with the RTX 4000, and that gives us basically like 2070-ish GeForce lineup capabilities on the card with all the encoding. So this was a really good fit for us. And again, this card's probably about $1,000 list. For memory, we went with 32 gig DDR4, CAS 3200. I'm sorry, CAS 15 with clock speed of 3200. Because we went with Ryzen, we want to be sure that our memory was fast enough so we didn't throttle anything on the CPU. And this was, what we decided to go with. And for storage, multiple things. Our OS is run on 1 terabyte NVMe's. We use local storage with 2 terabyte M2 NVMe's. So yes, there were the 2. They don't have the 4 yet though. And for recording, we use both 1 terabyte SATA SSDs, and we use 6 terabyte 7200 RPM physical drives. And, both of those work really well. But I think with all the specs and everything else aside, there's one thing that I think is really important for everybody to remember. And that's that RGB lights make everything faster. So whatever you build, trick it out with lights. It seems to be the key thing to having a performance system. It's very much like racing stripes on a car. They go faster. Same thing with computer technology here. So that's everything. Hopefully you found this useful. And I want to make a point that even if you're not looking to build your own system, and unless you're really confident and this is something you're going to depend on, it's not something I would recommend. I mean, I've been working around computers for quite a while, and I still depend on people that are really immersed in, the hardware side to advise me on how to put systems together for different use cases. So it's something that, if you want to do it yourself, that's great. Yep, streaming bling, absolutely. So and what's great is they've actually combined lights with cars now, and you get cars with this lighting and pinstripes. So it's like, wow, they must be super fast. But so this is something where these are questions you should ask, even if you're going to have somebody else build it. And some of these things are compromises. Do I spend more on getting more memory? Do I spend more on a better GPU, a better CPU? So if money's no object, it's pretty easy to put together an ultimate system. But for most of us that are using this as our business, and we have to hit a return on investment, we have to figure out what the balance is. So hopefully this gave you enough information to ask the right questions, to sort of weigh these appropriately, and then decide what makes the most sense for you. So thank you for sticking around for this long show. I know this ran way over. It's over an hour. So my apologies, but hopefully, it was worth it. We will be sticking around for an after show. If anybody has any questions or want to dive deeper on any of this, want to remind everybody that next week's show, we're going to be talking about video replay, but I want to look at it from the perspective outside of sports. So everybody knows and uses it that's involved in covering sports or esports. But I think there's some interesting use cases and workflow efficiencies that it can bring to traditional productions that a lot of us do day in and day out outside of sports. So we're going to talk about that next week. So thanks again. Uh, we will wrap this up, go dark, and then come back for the after show. And if you can't make that, I'll see you next week. Take care, everyone. Hi, everyone. How are you? So thank you for sticking around. I apologize that show ran so long. When you do sort of the timing in your head for what the slides will take, you don't always calculate this right. But I guess anybody that's actually done a conference sort of knows that speakers go up and they've got their half-hour talking slot, and there's 6 slides in a 12-slide presentation at 25 minutes. So I sort of ran into the same thing. So apologies there. But this was an interesting show to put together because a lot of what we took from this was things we've learned from working with different clients and putting systems and helping install studios. So the thing though that I want to emphasize is that everybody's going to have to deal with sort of the realities of with the realities of budget and the types of productions they do, the clients that they are going to be dealing with. So when you build a live streaming system, uh, so people need to know it all makes. Yeah, I mean, Richard's point is really right. The there are a lot of details that go into building these systems, and a lot of compromise. I think that's probably the biggest thing. It's knowing where to make the compromises that make sense. It's sort of like any big institution. Uh, the fact that something is good doesn't mean it's worth spending money on. There are a lot of good things, and we just have to make choices. Jeffrey, thanks a lot for joining us. Yeah, it's always great to have you here, and I'm going to make sure we hook up because there's some cool stuff that hopefully we can do together on the show going forward, and a few interesting things that I like to talk to you about. So we'll touch base on that. But when you pull these systems together, you are going to have to decide. I'm not going to go and get a 128 core Threadripper. you know, I may love to, but spending $4,000 on a CPU is probably not the best spend for the return I'm going to get from business. So excellent, Jeff. Thanks. Uh, so it's really making those compromises. I think if I were to steer people, it's and the reason I like AMD so much is AMD really has great bang for the buck, and that 8-core CPU is really, I mean, it's like under $350 for that with the cooler and everything. So that puts you in a really nice spot with a lot of compute power at the CPU end. And if I had to spend an extra $200 as opposed to spending that necessarily going to an Intel with the 9900 line, I would put that in my GPU and sort of upgrade the GPU there. Uh, but probably the first thing is make sure you have enough memory. I sort of did some of this backwards when we were talking on the show, but you should start by saying, I got to make sure that at a minimum I have enough memory, even if it's a little slower. Your system would be a lot slower if you don't have enough memory for all the things you need to hold in it, and you have to start swapping to disk. And then move out from there. The reason I talk about swappable drives for storage, though, is again, these are things of utility and compromise. Sometimes, sometimes the worst thing you can do, Richard. Yeah, the i9 is they're definitely cool chips, but they are pricey, and I do believe that some of the i9s come without the GPU embedded GPU, the integrated GPU components. So, but when I looked at those, I wasn't sure they were that big a difference in price. So I'm not sure that, you come back and say, oh, well, it's, a lot cheaper if I don't do that and buy a GPU. So you're not necessarily saving much. And, but I'm not putting down the Intel line per se. I just think that bang for the buck, AMD is probably in the best position in the market right now. And if I had to spend, I spend in making sure I have enough memory and upgrading the GPU because that's something where you'll probably get the most benefit from. And because our live streaming systems typically do multiple things, it may be your editing system. And if you're running something like DaVinci or Premiere, you're going to get better performance out of the higher end GPU. So it's sort of thinking of not just the workflow of your live streaming, but also the entire workflow around everything you do as a business and what you have to do to, for production things for end clients. So probably a pretty, broad set of things to consider. But, you know, the great thing is that you can definitely put together a really good live streaming system for under $2,000 and a very serviceable one for less than that. Uh, and it's something that I definitely would, if you're looking at upgrading, first look at pieces and components. But if your architecture is really old, don't invest good money after bed. Go into a new system. So, John, let's see. My 2 cents. Uh, yeah, absolutely. I mean, John's point is very well taken. The getting great monitors is another part of a live streaming rig. Uh, we were just part of a production last night that ran nearly 5 hours, and it was the second in two productions they did that day. The client did that day. So the thought of staring at a junky monitor for 5 hours, especially if you're using it to make judgment decisions around, yeah, I wouldn't want to be doing that. These eyes are bad enough. Age has taken their toll, but I don't need extra bad pixelized monitors that smear and streak all the time to add to the difficulty. So that's a very good point. But I wouldn't invest like if you're a system and it uses DDR3 memory, and if you need to, certainly upgrade that. And things like new disk storage, going to SSDs, those are obvious things. You can do that, and that investment moves forward. But I wouldn't look too heavily at those for anything that you can't really bring forward. So GPUs, in some cases, that would be a good investment, though, based on what's available in the PCI bus bandwidth. On the older systems, you may not get as much benefits as you think from the better GPUs. So again, these are things you can balance, but it probably makes sense given computer technology moving down a fairly steep curve, sort of the Moore's law, price performance curve, to at least have that as a consideration because what you can get at really reasonable prices, for a professional space is something to consider. Uh, so yeah, Richard's asking about Soltaire, rusting out the computer parts. Anything that has contacts is definitely susceptible. Uh, where you have advantages is when things are soldered on and industrially, and the rosin that sort of protects the connection. Uh, but over time, metal surfaces will get corroded out via rust. So especially things on the outside, less so on the inside. But this sort of brings up another point. The other thing to consider as you look at components is where are you packaging them, and what do you need to do with it as a physical end unit. So thermals are really important. Having great components inside your system uh, won't help if the system constantly overheats. And in fact, most computers do something called thermal throttling. So the performance of CPUs and GPUs will throttle down if the system gets hot, if the component gets hot. Uh, and so you lose a lot of benefits. So cooling becomes really important. And then cooling dictates the types of cases you can put things in. Uh, so, okay, Dennis is asking about eGPUs, and I did mention that with the you know with the people that are using like Wirecast or OBS on a Mac. So the two ones that you mentioned is the Blackmagic, which is an all-in-one. It comes with a AMD GPU in it. I forget which one it was. I think it's the 560 or 570. I'm Oh, 580. Okay, somebody's whispering in my ear here. That's the 580. So yeah, so that's something that isn't very high end. So if you purchase that, you're sort of getting that as a bundle. Uh, the Razer, I mean, there's two. There's a Razer and the Razer Chrome. I don't think Now the Razer Chrome has LED lights in it, so obviously it's faster, and it does have a bigger power supply in it. But I don't think there's a lot of difference. And the Razer Chrome is $399, and the Razer unit itself, I forget the name for it, is $299. So those are good, but definitely if I were to pick, I'd be going on the Razer side and buy my own uh, GPU for that. And if you're not Mac, I'd probably be picking something in the NVIDIA product lineup to use. It's but again, it's what you're most comfortable with. If you would prefer to buy something sort of all in one that you just take out of the box and plug in, that's cool. The other thing is the case on the Blackmagic does look really nice. So as an eGPU, that's a pretty nice thing. But you're not going to get as much throughput as you would from an internal card. So if you have a PC, definitely you're not really going to gain much by using this over a Thunderbolt, a GPU over a Thunderbolt 3. So uh, Windows-based systems definitely go internal. For Macs, I would probably go to the Razer lineup and go with probably a higher end uh, GPU in the AMD lineup, the Radeon lineup, just to just to give yourself the best bang for the buck. But again, you know that's a financial decision. I'm forgetting exactly what the Blackmagics cost, but I think they are considerably more than going with the Razer and buying your own. So something to consider there. But the other point I was making about thermals, that means you got to handle cooling. Cooling is multiple ways to do it. I mean, people in the gaming world use water cooling. I'm not a fan of doing that for something that my livelihood depends, especially if I ship it around. So I would probably keep what I'd want to do in a system to sort of traditional, ambient cooling. And you also have to recognize that cooling creates noise. So at what point does noise? Uh, so yeah, the eGPUs, both of them would work fine, but I think you get more value out of the Razer and buy your own. So everything that we've talked about here, I think, is it comes down to just sort of making the comments. You got to compromise on cooling. Uh, that's a bad thing to compromise on. Compromise on noise. So let it be a little louder, because the more quiet the cooling, the better it is for the more expensive it tends to be. So all things to consider. Your form factor, your cooling, and then the right compromiser components. So, all right, if we don't have anything else here, I'll probably wrap this up. This has been a very, very long show, but I thank everybody for sticking around, and hopefully it helped answer some questions for you guys. But if there's some follow up, just drop it in the group or the page, and I'll get back to you. So, all right, everyone. Until next week, have a good one. Thanks a lot.